Welcome back, children. So in today's class we'll study about radioactive disintegration law. Hope you remember in the last class I told you about radioactivity and the different types of decay, that is alpha, beta and gamma decay. So I told you that a radioactive substance spontaneously disintegrates to other elements by emitting alpha, beta and gamma rays. So in today's class we are going to discuss about a law which is related to it, and it is called as radioactive disintegration law. So we'll try to explain the radioactive disintegration law and how to express it in differential form, logarithmic and exponential form. After that we'll also go through the half-life and mean life of a radioactive substance, and I'll end up this PPT with activity and its units. So let us first begin with what is this disintegration law. Look at the statement. So as the statement says, the rate of disintegration of a radioactive substance. So here the meaning of rate of disintegration is, say we started our experiment with N0 number of uranium or any radioactive substance. As time increases, some of the uranium nuclides will disintegrate into other elements to attain stability. So the number of uranium atoms or the radioactive nuclides start decreasing with time. So the decrease in the number of uranium or the radioactive nuclides, I am writing it as minus dN in a time interval dt. So rate of disintegration is minus dN by dt. So the disintegration law states that the rate of disintegration of a radioactive substance is directly proportional to the number of radioactive nuclei present at the given instant. Okay, so if N is the number of radioactive nuclides at a given instant, N0 is the initial number of radioactive nuclides, then as per the disintegration law, you can express it in mathematical form as minus dN by dt is proportional to N. When you remove the proportionality, okay, we are writing a constant, and this constant is represented as lambda. So this equation, that's minus dN by dt is lambda into N, is nothing but called as the law of radioactive disintegration or radioactive disintegration law. So I repeat, minus dN by dt is lambda into N. Lambda is called the disintegration constant. So because this is expressed in differential form, now we'll try to modify it into logarithmic and exponential form. So let's see how to change it. Look at the expression. To get it in logarithmic form, we start with the disintegration law. The first statement says minus dN by dt is lambda into N. So bring N to the left hand side and dt to the right hand side. dN by N is minus lambda into dt. So I want to remove this differential. So integrate the relation, put the limits. N is starting from N0 and after t seconds it becomes equal to N. I repeat, when t is 0, N is N0. After t seconds, the number of radioactive nuclides remaining is capital N. And we know integral of 1 by N into dN is log N, natural logarithm, which is written as ln here. So ln of N from N0 to N is minus lambda into integral of dt is t from 0 to t. So when you put the limits, log N minus log N0 is minus lambda into t, or log N by N0 is minus lambda into t. So this equation we call it as the disintegration law expressed in logarithmic form. Actual equation is, as per the definition, it's minus dN by dt is lambda into N. But when you modify it into logarithmic form, you get the expression log N by N0 is minus lambda into t. Now from here we are converting it into exponential form. So as you already have the logarithmic form, applying antilog on either sides, N by N0 is e to the power minus lambda t, or N by N0. Okay, this is the fraction of the radioactive nuclides left undecayed after t seconds, is equal to e to the power minus lambda into t. Okay, where t gives the time for the ratio to reduce to N by N naught. So now that you know the three different forms, one is differential minus dn by dt is lambda into n, another is logarithmic, log n by n naught is minus lambda into t, and exponential form n by n naught is e to the power minus lambda into t. Now look at the different graphs. Okay, so observe the graph. So this is a graph plotted between the number of undecayed nuclei versus time. It is an exponential graph because n is n naught e power minus lambda t. As time increases, number is decreasing exponentially with initial value as n naught. Okay, this is the initial value. As time is increasing, this number will start decreasing exponentially. So this is an exponential decay curve. Now look at one more graph. This is also between n naught, n number versus time. That means number of radioactive nuclei left undecayed versus time for three different disintegration constants. Okay, you can observe the curve. Okay, the upper line indicated in red, the second line is indicated in blue, and the last one is in the brown. Depending on the values of lambda, the curve shape is going to change. Okay, the one which is steeper has large value of lambda, and the one which is less steep has a smaller value of lambda. So looking at the curve, you can find out what will be the value of lambda for different radioactive nuclides. Now look at one more graph. Okay, this is a graph plotted between log n versus t. Okay, just now we have written that log n minus log n naught is minus lambda into t. So if you write log n, it will be log n naught minus lambda t. Log n is taken on y-axis, time on x-axis. It is in the form y is equal to c minus mx, okay, which is a straight line with a negative slope and a positive intercept. Okay, so intercept is log n naught. That means when t is 0, the value of initial value is log n naught, and as time increases, it is a straight line with a negative slope, and you can remember this slope gives you the value of lambda. That means since slope is negative, I am telling you the magnitude of the slope will give you the disintegration constant. You can remember the two graphs. One is n versus t graph, another is log n versus time graph. So this is regarding the radioactive disintegration law. Now that you know the radioactive disintegration law, let's look into half-life of a radioactive substance. See, in the previous graph, when you studied n versus t, as time becomes infinity, at t equal to infinity, n naught reduces to 0 because it is not touching the x-axis. Graph is becoming, or the graph touches x-axis at infinity. Since we do not know the time when the radioactive substance is completely disintegrated, we try to define one more time called as half-life. So this half-life tells us the time interval in which the radioactive substance reduces to half the initial amount. Say we have initial amount as n naught, the time taken by a substance to become n naught by 2 is nothing but called as t half. So you can see the equation, t is equal to t half when n becomes n naught divided by 2. If you put these conditions in this disintegration law, that is n is equal to n naught e to the power minus lambda t. Okay, so put the two conditions. N has become n naught by 2 on the left hand side, which is n naught e to the power minus lambda into t half. So n naught will anyway get cancelled here. Okay, you can cancel this n naught on either sides. 1 by 2 is e to the power minus lambda into t half, or 2 is equal to e power lambda t half. Apply log on either sides and simplify. You get t half as log 2 by lambda. Okay, it's a natural logarithm. Convert into common log by multiplying with 2.303, and the value of log 2 to the base 10 is 0.3010. It comes out to be 0.693 divided by lambda. Remember this relation, T half is inversely related to disintegration constant. and is equal to 0.693 divided by lambda. This is called the half-life of a radioactive substance. So in one half-life, 50% is decayed and 50% will remain. Now one more life we are going to study for a radioactive substance apart from half-life. It's called mean or average life. So look at the definition first. It is a ratio of sum of the lifetime of all individual unstable nuclides to the total number of unstable nuclides present. So if I express it in integral form, T mean is equal to integral of T into dn by integral of dn. So we know n is n naught e power minus lambda into T. So you can differentiate and get the value of dn, put it in the relation, and by integration by parts, okay, if you integrate it by parts, then you will get the solution as 1 by lambda. Okay, I am avoiding the derivation here. You can remember the T mean obtained by integrating this, integration by parts if you apply, the final equation comes out to be 1 by lambda. I repeat, T half is 0.693 by lambda, while average life is 1 by lambda. Now look at the relationship between the two lives. One is half-life and the other is mean life. So from the previous two equations, we can write T half as 0.693 times of T mean, or opposite, T mean is equal to 1.44 times of T half. Okay, you can remember these two relations because we have already derived what is T half and T mean. Then remember these 2 points. In one half-life, 50% of the radioactive substance is decayed and 50% is undecayed. Now let's see what percentage is being decayed and what is left undecayed in one mean life. Okay, when you calculate, it comes out to be 63% is decayed and 37% remains. But let's see how is it obtained. We know n is n naught e power minus lambda T. So n is equal to n naught e to the power minus lambda. I took T as one mean life. Okay, just now we have derived what is T equal to. If T is 1 by lambda, okay, if you substitute the value of T in the disintegration equation, n is equal to n naught e power minus lambda T, we will get n is equal to n naught divided by E. The value of E is 2.718. Simplify it, it comes out to be 0.37 n naught. Remember, this will give you the number of undecayed nuclides, which is 0.37 times of n naught, or I can say 37% is remaining undecayed. So what percentage has decayed? 100 minus 37, that's 63%. So in one mean life, 63% is decayed, and in one half life, 50% is decayed. So these 2 points you can remember. So this is regarding radioactive disintegration law, half-life and mean life. Now coming to one more term called as activity. Rate of disintegration. Okay, we have seen that minus dn by dt is called rate of disintegration. This itself is called as activity or radioactivity, which is represented by the letter capital A. In a few books, it's also represented as capital R. Okay, both of them mean the same. R is equal to minus dn by dt, or capital A is equal to minus dn by dt. So this is called activity of a radioactive substance. Now you can express it in different forms again. Since we know n is n naught e to the power minus lambda T, differentiate it minus d by dt of n naught e power minus lambda T. N naught is a constant. Integral e power minus lambda T is e power minus lambda T into minus lambda. Minus into minus will anyway get cancelled. We are left with this relation. A is equal to lambda n naught e power minus lambda T, or capital A is a naught e to the power minus lambda T, where a naught is called as initial activity, which is lambda into initial number of radioactive nuclides, that is n naught. So just like we have your disintegration law, n is equal to n naught e power minus lambda T, even activity is also equal to a naught e to the power minus lambda T. Both of them are exponentially decaying with time. So the graph obviously will be similar to n is equal to n naught e power minus lambda t graph. This is the initial amount. A naught is the initial activity. As time increases, activity is exponentially decaying. It meets the axis at infinity. But important here is the various units of activity. Okay, let's see what are the different units of activity. SI unit is becquerel. 1 becquerel is equal to 1 disintegration per second. Hope you remember radioactivity phenomenon was first discovered by a scientist called Becquerel. I told you we call radioactive rays, alpha, beta and gamma rays also as Becquerel rays. So the unit of radioactivity is named after him as Becquerel. So 1 disintegration per second is 1 becquerel. Apart from this, there are two more commonly used units, that's Curie and Rutherford. 1 Curie is 3.7 into 10 power 10 disintegrations per second, and 1 Rutherford is 10 power 6 disintegrations per second. So all these three are called as the units of activity. So altogether in today's class we have seen what is radioactive disintegration law, how to express it in logarithmic and exponential form, the various graphs related to the number of undecayed nucleus and time, log n versus t, what is half-life and mean life and their interrelationship. At last we ended up with what is activity and its units. So in the next class we'll be doing some numericals related to activity and disintegration law. So that's all for today. Thank you.